Very good morning to everyone. Now we are basically in the last class what we did, we talked about the various types of separation processes, classification of the separation processes. They will be broadly categorized into two categories. One is equilibrium based separation processes, another is the rate governed separation processes. And we have seen what are the various gamuts of these separation processes and what are the driving forces and the various other principles roughly involved in these two separation processes broadly. We have also discussed the some of the unit operations in equilibrium governed separation processes, for example, distillation, absorption, adsorption, drying, so on and so forth, and also some rate governed separation processes like membrane based processes like reverse osmosis, dialysis, ultrafiltration, so on and so forth. So, therefore, in this particular course we will be taking those processes which are not conventional and which are not traditional. For example, we will be talking about, so let us identify the novel separation processes. Which are not traditional and conventional. Okay. So, these are basically number one is membrane based processes, number two chromatographic separation processes, number three electric field assisted separation processes, number four supercritical fluid extraction, so on so forth. So, therefore, these electric field assisted separation processes are quite important because they have you can use them for separation of solutes which are charged. For example, it has tremendous application in the protein separation and fractionation of the protein from the protein mixture. So, therefore, there are some more topics there in the novel separation processes. We will be basically looking into them in detail for in the now onwards, and our course is generally oriented about the description as well as the design of such processes. So, after doing this course you should be able to design a separator which is suitable for a particular process. Okay. So, now on we will be next we will be doing the membrane based separation processes, a detailed study of various processes and the other things those are involved in such processes. So, we start with membrane based separation processes. Now, let us first look into the definition of a membrane. A membrane is basically an interface. It is an interface that separates two phases. And allows preferential transport of various species. So, it is basically either a polymeric phase or an inorganic phase that separates two phases, and it allows a preferential transport of a particular species through it. So, therefore, that causes the separation. If one species is preferential, is more transported, if the rate of transport is more compared to the other species through the membrane, then the downstream it will be enriched in that particular species, that causes the separation. Now, we are talking about the and there are let us look into the various steps of membrane castings. How to prepare them. and we are basically talking about the polymeric membrane. Now, the common polymer that is used for casting the membrane is cellulose acetate, polysulfone, polyacrylonitrile, polyether sulfone, PVDF, polyvinyl difluoride. This cellulose acetate is used for casting the reverse osmosis membrane. For example, cellulose acetate polyamide PA. Polyamide is also used for casting the reverse osmosis membrane. Polysulfone membranes and polyacrylonitrile polymers are used for casting the ultrafiltration membrane. Now, all these membranes are hydrophilic, and polyether sulfone is another polymer which is quite hydrophilic, and that will be these are generally used for casting reverse osmosis, ultrafiltration, nanofiltration and microfiltration membrane. We generally look for a property which is typical for the membrane, which will be very useful for separation of solutes. What is that property? The property is hydrophilicity. The membranes are supposed to be very hydrophilic, then it will be more selective for a particular species. For example, most of the pollutants are hydrophobic in nature. For example, organic pollutants and dye stuff and other pollutants, they are generally hydrophobic in nature. So, we would like to have a membrane which will be hydrophilic. So it does not like the environment of hydrophobicity. So, it does not want to have the pollutants, but but it will be having a great liking for the water. Okay. So, therefore, water will be preferentially transported through it, and you can expect a pure water solution in the downstream or in the permeate stream of the membrane. So, therefore, hydrophilicity is a very important property, and a polymer polyether sulfone is generally used for having imparting more hydrophilic characteristics in the membrane matrix. PVDF is a polymer which is hydrophobic in nature. So, using PVDF polymer, one can have hydrophobic membranes, and hydrophobic membranes have various applications in case of membrane distillation and osmotic distillation and things like that. Those applications we may be looking them in detail later on in this class. So, therefore, various polymers of different kinds are utilized for casting the membrane, and selection of these polymers are generally done for imparting important and desirable properties to the membrane. Now, let us look into the various steps involved in the casting process. Solvent. A typical solvent is acetone, is added to the polymer. Polymer preparing a viscous solution. Then it is put on a plate. The solution, viscous solution, is put on a plate, glass plate, and place another plate on top of it. Okay. The gap may be around it is pretty small, around 0.25 millimeter. Okay. Then third step is give a one dimensional motion on top plate. What it results? It results a thin film on the bottom plate. Okay. Then you take out the bottom plate and place the bottom plate in ice water bath. What it does, the polymer film becomes solidified. Okay, this is known as, and it gets detached from the plate. Film is detached from the plate. So, that is basically the membrane, and this technique is known as phase inversion technique. Why it is called phase inversion technique? Because the phase is just inverse. Okay. Initially, we started with a liquid viscous phase, and then when we place it in water, it becomes solidified. Okay, and the phase becomes from liquid to solid. So, it becomes a different phase, and the film gets separated from the plate, and that film is basically a membrane film. Now, there are some more steps are there. We heat treat it. Heat treat the film either in hot water, okay, and this process is known as annealing. Now, during this process, the solvent gets evaporated. From the polymeric matrix. During evaporation, it creates the pores. Now, these pores are this results in pore structure or pore network. These pores can be straight, they are basically interconnected, may not be straight pores, straight cylindrical pores. Okay. They may be interconnected, they may be tortuous. So, there will be some kind of tortuosity in the membrane matrix, and these pores are formed. Now, there are typical. I will just write down the typical casting conditions for casting a reverse osmosis membrane. Casting solution, cellulosic acetate, let us say 25%, formamide 30%, acetone 45%. This is the polymer, this is a solvent, acetone is another solvent, and casting temperature is 25 degree centigrade, and evaporation time (1 minute). What is evaporation time? Evaporation time is the time duration for evaporating the solvent. So, that means when you put in the ice water solution, you just put in the ice water bath for 1 minute. So, during that the evaporation will take place, and pore network will be produced. Now, there is a, so this is a typical procedure and typical casting conditions for casting a membrane film, but there is a problem in it. The membrane film that you are producing out of this method is very fragile. Okay. So, there should be some mechanical support given to this film. So, what is generally done? This film is cast over a non-woven fabric, non-woven polyester fabric, okay. Over a non-woven polyester fabric, this film is cast, and it is the thickness of the film is generally maintained by something called doctor's blade or a screw gauge. Okay. That maintains the thickness of the film, and the thickness will be in the order of, let us say, few microns, 40-50 microns, like that. Now, this polyester fabric gives the mechanical strength or mechanical support to the polymer film, because most of the operations are high pressure operations. For example, reverse osmosis is a very high pressure operation. The typical operating condition of reverse osmosis is more than 25 atmosphere. For nanofiltration, it will be more than 15 atmosphere or roughly around 10 to 15 atmosphere. For ultrafiltration, the pressure is operating pressure is about 4 to 6 atmosphere. For microfiltration, it will be less. So, we will be talking about all these typical conditions, etc., and categorization of various membrane based processes later on. So, that should be kept in mind. Now, these types of barriers, the membranes are also known as the porous barrier. These type of barriers can be of two types: homogeneous and heterogeneous. Okay. Homogeneous is basically the membrane is of a particular polymer, single polymer, forms the membrane. In the case of heterogeneous, or it is also known as asymmetric, there are two films of polymer are cast one above another. Why it is cast one above another? Now, basically the membrane based processes, there are two outputs you are looking for. What is the first output? You are looking out at the productivity of the process, how fast the process is, what is the volumetric flow rate or filtrate rate you are going to get. If you get something very low, let us say 1 liter per meter square hour, that means if you provide 1 meter square area, you are getting 1 liter in 1 hour, that is very low, and it is not feasible for a practical operation. But if it is 200 liter per meter square hour, then it is quite feasible. So, that is called the productivity of the process, and this liter per meter square hour is known as the volumetric permeate flux or the filtrate rate, volumetric filtrate rate. So, that is the productivity of the process. Second aspect you are looking for is the quality. So, that is the quantity. So, second aspect is what is the quality of the permeate, what is the concentration of solute that you are going to expect in a particular species. If it is a case of pollution control, you must be looking for a particular threshold value of a particular species. Let us say it should be, the concentration should be less than 1 ppm or something like that. If it is a recovery problem, then you must be looking for the concentration of a particular solute in the permeate stream must be above some concentration. Okay, so, depending on the situation, you will now the permeate flux or the productivity of the process is very important as far as the feasibility, practical feasibility of the process is concerned. Now, this permeate flux is inversely proportional to the thickness. More with the thickness, more mechanical resistance it will be offering against the flow rate. So, productivity of the process or permeate flux is inversely proportional to the thickness of the membrane. Okay. So, if you lower down the thickness of the membrane, the productivity becomes very high. So, you can go for higher productivity of the process. So, how it is done? First, on a non-woven polyester fabric, you put a coating of, let us say, polyacrylonitrile, okay, or polysulfone, something like that. So, these polymers will be cast on as a film on the polyester fabric with let us say higher pore size. Then you cast another film of, let us say, cellulose acetate or polyamide over it. Okay. So, basically that will create a skin over the higher pore sized polymer support. So, there will be a skin, and at the lower end there will be another polymer, let us say this is polyamide or cellulose acetate skin, and this is, let us say, polysulfone or polyacrylonitrile base, and below here you are having the polyester fabric. Okay. Now, actual membrane is basically this skin. This is the actual membrane. Since this thickness is much lower compared to the thickness of the supports, that will be, then you can expect a higher productivity of the process. This is known as asymmetric or non-homogeneous membrane. So, therefore, in order to increase the productivity of the process, asymmetric membranes are quite important, and these asymmetric membranes are invented in the during 1970s, and during the invention of the asymmetric membranes, the membrane based processes are becoming more feasible as far as the industrial or practical use is concerned. Okay. Now, let us look into the types of motions. Types of motions, you will be motions of molecules through membranes one can encounter in the membrane. First process is called permeation. What is permeation? Permeation has three distinct steps. One is dissolution, another is diffusion, third one is desorption. Okay. Here we are talking about almost non-porous membrane, or pores are very small in case of reverse osmosis and nano filtration. Here the solutes are getting dissolved in the dissolution step. Solutes are getting dissolved in the membrane phase because of the concentration gradient, and because of the concentration gradient only, it will diffuse from the upstream to the permeate side, feed to the permeate side through the membrane matrix. Then because of the concentration gradient in the permeate side, the concentration is, there is nothing almost, and it gets dissolved in the permeate side. These three steps, including in total, they are called permeation mechanism. Second one is Knudsen diffusion. D by lambda is less than 0.2. D is the pore diameter and lambda is the mean free path of the molecule. If it is less than 0.2, this mechanism is called Knudsen diffusion, and these are basically transport of gaseous species under rarefied conditions. Third one is convection. If d by lambda is greater than 20, then pure convection will be taking place under the pressure gradient. Okay. So, these are three typical various different mechanisms that will be coming across, you will be coming across in various membrane based processes. The permeation will be typical operation or typical mechanism, transport mechanism for reverse osmosis and nano filtration. Convection and for ultrafiltration, both diffusion and convections will be more or less predominant. As you go towards the more pore size of the membrane, means relaxed pore size of the membrane, the mechanism is transferred from diffusion to the convection, right. For lower molecular cut of ultrafiltration membrane, diffusion may be predominant. For let us say around 40,000 or 50,000 cut of ultrafiltration membrane, both are equally good, and for higher cut of membrane, let us say 1 lakh or 2 lakhs cut of ultrafiltration membrane, convection is the only mechanism. For microfiltration membrane, convection is the only mechanism. Okay. Now, probably we are in a position for categorization of various membrane based processes. The first process we will be talking about is reverse osmosis. Okay. So, in the last class I gave some idea about reverse osmosis. Now, let us look into the various characteristics of reverse osmosis process. first of all, it has the smallest pore size. The pore size is pretty small and it will be in the range of 2 to 10 angstrom. Second is, since the pore size is 2 to 10 angstrom, it will be used for separation of very low molecular sized material. Okay? That means you are going to separate small solute particles which will be having a molecular weight typically less than 100. That means various types of salts. Okay? The sodium chloride will be having a molecular weight around 58.5. Now, since the pore sizes are very small, the osmotic pressure will become predominant in such cases. And if you that we will talk about it later on, the osmotic pressure has two characteristics. It is directly proportional to the concentration, that's why it is known as the colligative property. It is inversely proportional to the molecular weight. So therefore, if you encounter a solute which will be having a very low molecular weight, its osmotic pressure becomes very high. For higher molecular solutes, the osmotic pressure becomes low and it is not very important. So here, because of that particular property, since we are talking about the small sized solute particles, the osmotic pressure becomes pretty high. Now, in case of reverse osmosis, as we talked about in the last class, that you have to apply pressure in the feed side to overcome the osmotic pressure, right? Then only the first drop of permeate will be coming in the downstream side. So pressure requirement in reverse osmosis becomes highest because to overcome the very high osmotic pressure. So pressure requirement is in the order of 25 to 40 atmosphere. And main transport mechanism is permeation that we just discussed. Is permeation, and typical example or application is filtration of saline solution. That means salt solution. So it is tremendously useful in case of desalination purposes. So that goes for the reverse osmosis. The next filtration process or next category of such process is nano filtration. Here the pore size are slightly higher than reverse osmosis. The average pore size will be in the range of 5 to 20 angstrom, and the particles. So therefore, you can, since the pore sizes are slightly higher, one can expect a high pore to separate the particles of higher molecular weight. So molecular weight of the particles to be separated will be in the range of 200 to 1000. Okay. Since the pore size is higher and the molecular weight of the particles to be separated is higher, its osmotic pressure will be lower. So therefore, pressure requirement will be slightly lower in this case. Now, a good and it causes a partial retention of salts. Okay. A good reverse osmosis membrane is termed to be a very good reverse osmosis membrane if it can reject a sodium chloride solution to the tune of 95 to 98%. If sodium chloride is separated to the extent of 95 to 98%, that particular reverse osmosis membrane is supposed to be a good reverse osmosis membrane. On the other hand, in case of nanofiltration membrane, the monovalent salt, for example sodium chloride, should be separated in the tune of 65 to 80%. So it is called partial separation or partial retention of the salts. So the difference between the nanofiltration and reverse osmosis is very thin, okay, and it is very very flimsy. The only difference is the salts, monovalent salts, are partially rejected by the nanofiltration membranes in the tune of 60 to 80%. On the other hand, in case of reverse osmosis, the monovalent salts are highly rejected by the membrane to the tune of 95 to 98%. So this is the main difference between the nanofiltration and reverse osmosis. The applications and examples of nanofiltrations are dyes, separation of dye molecules. Dye molecules will be having, generally they have the molecular weight in the range of 200 to 850 or 900. Okay, there are various dye solutions, dyes are there which will be having the molecular weight in this range. The small low molecular weight organics, I can give an example like polyphenols. Okay, they will be having a typical molecular weight between 400 to 600. Okay, they can be separated by the nanofiltration completely. So you can select a appropriate cutoff or characterized nanofiltration membrane and can separate out the polyphenols or dye. And nanofiltration has tremendous application in treatment of textile effluent. So it can separate out the dyes, but at the same time, in any textile effluent there will be, apart from dye, first of all the colorant dye, and dye, the color becomes very appealing even at lower concentration. So even if you have a concentration around 50 ppm, something like that, dye becomes colored. So for removal of dye, the color is basically one thing, and another is its polluting capability. Okay. So typically the dye textile effluent should be containing dye concentration less than 1 ppm. That is a typical norm. Also, the textile effluent contains very high amount of sodium chloride salt. Why? Because this is required. This is a requirement to fix the color on the fabric. Okay. So any textile effluent will be having a pH very high, sodium hydroxide and sodium chloride, sodium sulfide. These are the salts and alkali. So they are in the alkaline conditions. Okay. So the typical pH will be in the order of 11 to 13. Any textile effluent. So therefore, one has to separate out the dyes, as well as one has to recover the sodium chloride or NaOH, so that you can recycle them and can reduce the operating cost of the plant. So therefore, nanofiltration has now become a routine unit operation in textile effluent plants. At the same time, they are separating out the dyes, and in the permeate, so that means retentate contains most of the dyes, and the permeate contains sodium chloride and the other salts and alkali, and that is simply recycled back. So therefore, by using nanofiltration membrane, one can have a zero discharge plant even in the textile effluent process, textile industry. Okay, you can separate out the dye and reuse it, and in the same time in the retentate stream and in the permeate stream, you will be having a solution which will be rich in salt and alkali, that will be recycled in the upstream of the dye bath. Okay. Otherwise, nanofiltration is a typical process in the pharmaceuticals and other applications, dairy industries. The most important and most utilized process is ultrafiltration. Here the pore sizes are larger than nanofiltration membrane, is 5 to 20 angstrom. Okay. No, 5 to 20 angstrom was nanofiltration, so it will be 20 to 100 angstrom. Okay. The molecular weight of solutes that is separated will be in the range of 1000 to 10 to the 5, 1 lakh. Okay. And the pore size will be 20 to 1000 angstrom, and pressure requirement, since we are talking about the higher pore sized and higher molecular separation of a higher molecular solute, the pressure requirement will be less, and it will be 6 to 8 atmosphere. And the transport mechanism is a mixture of convection as well as diffusion. This is main plus diffusion. Okay. So, and it has a wide variety of applications and or examples. For example, one can have the separation of high molecular weight protein. Okay. The membrane can be utilized for separation or purification or fractionation. All the purposes can be served. One can separate out a particular solute. One can purify a particular solute by separating out water from the solution. One can fractionate it. Suppose you are having two solutes which will be having a molecular weight, let's say 60,000, another solute which will be having a molecular weight around 7,000. Then you can select a particular membrane, let's say 40,000 or 30,000 cutoff, that will retain the higher molecular solute in the upstream side, and it will allow the lower molecular solute in the downstream side. So, it can be utilized for the case of fractionation. So, protein separation, purification and fractionation, red blood cells, polymeric solutions, separation on purifications of polymeric solutions, they can be done under ultrafiltration process. Now, out of these all these processes, ultrafiltration and microfiltration are widely used. Now, we will be going to the next process, that is the microfiltration process. The first characteristic of microfiltration is pore size is very high, and it will be in the order of more than 1000 angstrom. Okay, 0.1 micron, 0.2 micron, 1 micron, 2 micron, like that. Okay, and the pore size is more than 1000, and the molecular weight of solutes to be separated is greater than 1 lakh, 10 to the power 5. Okay, and pressure requirement is lower, it is 2 to 4 atmosphere. An example is the filtration of clay solution, latex, paint, etc. Okay. So, if you just observe that when the pore size of the membrane becomes higher, the pressure requirement is going to be lower and lower. Okay. You do not require very high pressure for affect the separation. This is simply because if you are talking about the low pore sized membrane, then the osmotic pressure becomes pretty important and becomes very high. Okay. So, we have to overcome that, and then the pressure requirement becomes very high in those cases. Now, once we categorize various membrane based processes, we will go for certain definitions, and which are pretty important in whenever we will be doing the design and other, and we will be discussing various processes in the later half of the course. So, let us look into some of the useful definitions. The first definition is osmotic pressure. Okay. Osmotic pressure is denoted by the symbol pi, and I think we have discussed to some extent in the last class. I will discuss it again in more detail. Suppose we are having a chamber separated by a semi permeable barrier. Semi permeable means it is between the two species, it will be selective to a particular species. That means it will allow water, but it will not allow salt, and we will be having, let us say, same volume of water in both the chambers. Then let us say this is the solution side, we add some salt here, and this is the solvent. Solvent is pure water. Then the water activity is less in the solution chamber and more in the solvent side. So, water will be transported from the solvent to the solution side because under the driving force of chemical potential gradient. So, and after some time the equilibrium will be in effect, and say it may be after 24 hours, it may be after 36 hours. Finally, the level of water on the solvent side will go down and level of water in the solution side will go up. That will cause a hydrostatic development of a hydrostatic head rho GH, and this is nothing but the osmotic pressure. Now, since we have discussed in the last class that osmotic pressure is a colligative property. Colligative property means any property that will be depending on the amount of solute present in the system. So, that means if you increase the concentration of the salt in the solution side, the concentration difference will be higher. So, the water activity difference of water activity will be higher. So, more water will be permeating from the solvent side to the solution side. So, in that case the hydrostatic pressure or rho, the H delta H between the final equilibrium position of the in the solution side and the solvent side will be more. So, osmotic pressure developed will be more. So, therefore, osmotic pressure is directly proportional to the concentration of the solute, and osmotic pressure is inversely proportional to the molecular weight of the solute. So, therefore, if you are talking about a solute which will be having a lower molecular weight, the osmotic pressure is very high, and therefore, for dilute solution, pi is given as RTC by m molecular weight. This is known as Van 't Hoff relation. Okay. Now, for the it has been observed that for the salt solution, this is for the monovalent salt. For the divalent salt, I will let you know what is the relation for the divalent and higher valent salts. It is basically pi is equal to nu plus nu minus RTC by m. That means, for CaCl2, this is basically valency, nu plus is 2 and chloride minus is 1. So, you will be getting the the osmotic pressure will be slightly higher. So, therefore, for the salt solution, Van 't Hoff relation is good enough. For the salt solution, we can use Van 't Hoff's relation, either monovalent or divalent or multivalent. For the higher for other solutes like polymeric solution, protein solution, the Van 't Hoff relations can no longer be used, and Van 't Hoff's relation can be used only under dilute conditions. Okay. For these cases, Van 't Hoff relation can be used in dilute limit. Okay. For concentrated solution, Van 't Hoff's relation is cannot be used. One can go to the thermodynamics and can get the derivation that in such cases, for the concentrated solution, the osmotic pressure will be in the form of virial coefficients. Okay. So, in that case, osmotic pressure can be expressed in the term of a polynomial of concentration like alpha 1 c plus alpha 2 c square plus alpha 3 c cube, like that. Okay. So, in most of the cases, these relations are available in literature. Okay. People use osmometer. The osmotic pressure measurement machine instrument is called osmometer. They conduct experiments under various concentration and measure the osmotic pressure, pi versus C. Okay. These measurements are there, then it is plot, and the trick is you should not plot pi versus C, you should plot pi by C versus C. Okay. Then fit a polynomial. And express pi by C versus C as something like alpha 1 plus alpha 2 C plus alpha 3 C square. So, after multiplying C in both sides, you will be getting pi is equal to alpha 1 C plus alpha 2 C square plus alpha 3 C cube. So, therefore, why it is cast in this form is simply because if you put in this expression C is equal to 0, pi becomes 0. What does physically that mean? That physically signifies that if we have a pure water or pure solvent, the osmotic pressure is 0. So, if you plot pi versus C from the experimental measurement, then you will be having some residual osmotic pressure for if you put C is equal to 0, which goes against the physical principle. So, in order to corroborate the physical principle, the experimental result are converted into pi by C versus C in order to have a 0 osmotic pressure for pure solvent. Now, for membrane based processes, the osmotic pressure becomes very important. Why? actually any solution will be having its own osmotic pressure. For example, if we have a glass of saline solution, it will be, or let us say sugar solution, or let us say a cane juice solution, it will be having its own osmotic pressure. That means when you are having a glass of saline water, it will be having its own osmotic pressure, but you cannot realize the osmotic pressure. Why you cannot realize? Because osmotic pressure can be realized if and only if, that is very important, if and only if a semi-permeable barrier is present in the solution. Otherwise, you cannot experience the presence of, you cannot realize the presence of osmotic pressure. That is why whenever you are talking about a membrane based separation process, since a semi-permeable barrier is present in the solution itself, the osmotic pressure becomes very important. When you are drinking a glass of saline water, you are having an osmotic pressure, you are drinking it, but before that you are not feeling it. But when it is going inside the body, in the vessels, etc., all these are basically semi-permeable barrier. So it creates an increase in blood pressure. So therefore, the doctors always advise, don't take, if you have a heart problem, don't take water, don't take salt. You should decrease the intake of salt, because that will increase the osmotic pressure in the blood vessel and it may rupture. Okay. So osmotic pressure can be realized only in presence of a semi-permeable barrier, and that is why it becomes very important in case of membrane based separation process. Later on we will see, whenever we will be modeling such systems, the most important model is osmotic pressure model. Okay. The next important definition will be observed retention. It indicates selectivity of the membrane. That means how selective my membrane is. That means how selective my membrane is means how much solute it can retain. It indicates, physically it indicates extent of separation. This is defined as R subscript O, and it is 1 minus Cp by C naught. Okay. Cp is the concentration in the permeate, concentration of solute in the permeate, C naught is solute concentration in the feed. Okay. So this gives directly the extent of separation. That means you know what is the concentration of the feed solution. You can experimentally measure it. You can run the experiment and get the permeate or the filtrate and measure the concentration of it, and you will be getting the Cp. So by using this definition, one can get the extent of separation. This is known as the observed retention. Why it is known as the observed retention? Observed retention it is because the permeate concentration or the permeate stream, quality of the permeate stream is compared with the feed stream. That is why it is called observed retention. So therefore, there exists another counterpart of observed retention, that is known as the real retention. And what is the difference between the observed retention and real retention? The definition of real retention is 1 minus Cp by Cm. Cm is the solute concentration on membrane surface in feed side. Okay. So what it gives, basically the difference between the real retention and when it will be used and when the observed retention will be used. Observed retention will give you a direct measurement, because you do not know how to measure the surface concentration over the membrane surface, because it is in liquid phase. Now suppose you take out the membrane and dry it and measure the concentration and dissolve it, redissolve it, but that will not give you the real picture. Okay, because when you are taking it out, when you release the pressure, that means if you want to take the membrane out of the system, you have to release the pressure. When you release the pressure, some of the solutes that will be deposited over the membrane surface will be again redissolved. So that will not give you a direct measurement. So direct measurement of CM is really very difficult. What you can do, there are theories present so that you can have an estimate, or you can theoretically calculate what is the membrane surface concentration. In fact, membrane surface concentration will be always higher than the feed concentration. Why? Because it is a pressure driven process. Suppose this is the membrane and this is the feed concentration. You are pressurizing the system. Under pressure, solutes will be convected towards the membrane surface and they will be retained by the membrane. So there will be a sort of concentrated solution of the solute present near the membrane, or you can otherwise you can more technical term, you can say there is a development of concentration boundary layer or mass transfer boundary layer over the membrane surface, something like this. So there exists a concentration gradient starting from C naught up to Cm near the membrane surface, and Cm is always greater than C naught. Okay. So therefore, real retention is always, you can using this relationship and the definition of the real retention and observed retention, you can identify that real retention is greater than observed retention always. Now, why then these two definitions are used? Because in one definition it is directly measurable. Real observed retention is directly measurable, and you can say that my membrane is, let us say, it's rejecting 40% of the solute or 90% of the solutes. Then what is the use of real retention? The use of real retention is not in the direct observation, it is used in design of such processes. Why it will be used in design of the processes and the significance of the real retention, we will just discuss in the next class.